Hello my dears, how are you all? So in the last class we discussed about the different configurations and some derivations regarding the common emitter, common base, common collector configuration of transistor. And in the syllabus of sub-engineer, it is just mentioned as transistor, but I took very in detailed manner, and this table is very important regarding the transistor. It is a summary of the transistor, full. It's a summary of transistor. So never skip this table, my dears. Never skip this table. It's very important for the one word type of question. Okay, especially for sub-engineer, this is very important. That much important. In this table, you will cover everything. Let's check. So the important parameters in different configuration, CB, CE and CC, common base, common emitter and common collector, it's given in the table. It is first is input impedance, right? Input impedance. For common base it's low, and its common emitter is medium, and common collector it is high. Okay, and output impedance always high, medium and low. Voltage gain high, medium and low, and current gain low, medium and high. That we already know, right? Current gain for common base it's called alpha. Alpha is, we know that it's very low, less than 1. And medium for that common emitter, it is beta, right? It's beta, but beta we know that it is nearly in the range of 100, 200, etc. So it is high actually. So that is why medium. But common collector configuration we discussed about the gamma already, and gamma is the highest value ever, right? Among these three, alpha, beta, gamma is the highest value. That is why it is high. And power gain is nothing but, my dear, the product of the voltage gain and current gain. Okay, the product of voltage gain and the current gain is nothing but the power gain. So if you multiply high with low, you get medium. If you again multiply medium with the medium, you will definitely get a very high value. So this term you have to note. Power gain of common emitter is very high. That is why it is really useful, or it is really used in the transistor as an amplifier. Okay, transistor as an amplifier. Why common emitter is used? It is very high. But there is a problem with common emitter. That is, the output will be, you will learn. Okay, you will learn when transistor cascading, the output will be actually 180 degree out of phase with the input. Okay, so the common emitter configuration is nothing but very high. Okay, what is that? Power gain. This term you have to note it down. And common collector is nothing but, my dear, if you multiply the voltage gain low with the gain high, you will get a medium value. That's all. Only medium and medium multiply will give to very high, right? 5 into, okay, you know, it's simple mathematics, you know, no need to explain at all. So the term very important is, everything is important, especially the high low values now, that is more important. High low, low high, high low, these values are really important. And actually there is very shortcut for finding, remembering all this, my dears. In which manner I remember this is nothing but, first of all, we know that common base is the first basic, common base, common emitter and common collector. So EB, CB, CE and CC. So this order you got already. Next you just go for input impedance, because from the input side we are tracing the element, right? From the input side we are working, or we are tracing the circuit, right? So input impedance, output impedance. See the order: input impedance, output impedance, voltage gain, current gain. The product will be the power gain. So you got these 5 terms. Okay. Next, this term I have a trick. You remember like simply, okay, low, medium, high. Again reverse, high, medium, low. Again the same, high, medium, low. Okay. Next one, the first itself, low, medium, high. Okay. And the product will give the result, next one. So this only high, this is medium and this is medium. Simple, that's all, finish. That's all, finish. See, low, medium, high, LMH, HML, LMH, the same thing. and MHM. MHM, you don't need to worry, you don't need to remember this one. You simply multiply this. If you know the concept, definitely find the last power gain also. No need to remember at all, right? No need to remember. Is it clear, my dear? Is it clear? So this is very important term. Okay, very important term regarding the transistor configuration. Even if you miss the common emitter, common base, common collector configuration, derivation and all, but never miss this. You just mug up this in your own way. You just feed it to your memory, and definitely it will be helpful to you in the examination hall. Okay, definitely it will be helpful in the examination hall. So never skip this session, my dear. Okay, it's that much important. Okay, so with that I am going to wind up the transistor. Okay, I'm going to wind up the transistor. Okay, so next we are going to discuss another topic in the sub-engineer syllabus, which is diode rectifiers. Actually, the term rectifier and transistor together it is there. So the diodes and transistor rectifier together is there. So now we are going to diode. We already know that. So diode rectifier, that is nothing but the application of diode. So next is diode rectifiers. So before this, what is the need of a rectifier, my dears? What is the need of a rectifier? Rectifiers are used where DC supply is necessary. For example, for the working of a DC motor, for the working of DC generator, DC motor. I already discussed DC motor, and some DC requirement will DC cranes and all, right? Crane and all. So in that situation we require DC for battery charging. Of course, one of the very good example for the requirement of DC traction, my dears, DC traction. Okay, so in all these cases, all this situation, we required DC, and DC is not produced, right? DC is not generated. We generated AC with the help of some rectifier circuit only. We have to convert the AC into DC. So definitely we need some circuitry in order to convert AC from AC to DC, converter from AC to DC. So that circuitry is called nothing but the diode rectifier. So rectifiers are really meant to be applied in various situations in the daily life. We already discussed that. Okay, so there are two types of rectifiers, my dear. You know that definitely it is full wave rectifier and a half wave rectifier. So what a half wave rectifier do? You will consider first half wave rectifier. Half wave rectifiers. So what half wave rectifier really do, my dears? So it converts only a certain half cycle of the input supply that we applied. Okay, it converts only half cycle of the input wave, or it produces only half wave output with respect to input. Anyway, you can remember it converts only half cycle of the input wave, or it produces only half wave output with respect to the input. Okay, that is called the half wave rectifier. And next is nothing but the full wave rectifier. So what it does, what it do normally, full wave rectifiers, what it do normally, it converts the, or you can say that, okay, it converts full wave electrical input to output, or it produce the output in both the half cycle. It produces the output for both output for it converts the full wave electrical input to full wave electrical input to output. It fully convert the input cycle that we are given to the rectifier, or in other words, regarding the output, we observed in the output what happened. It produced the output for both the half cycle of input. It produces both the half cycle. Any definition you can. Okay, just it is simple as you have to you have a knowledge of what is happening there. That's all. No need to worry about the definition and all. Okay, so let us discuss one by one, my dears. So first of all, we are going to discuss about the half wave rectifier. Okay, first of all, we are going to discuss about the half wave rectifiers. Half wave rectifier. Okay. Half wave rectifiers. Okay. Listen, my dear. Okay, listen, let us discuss the half wave rectifier using a diode. Okay, so in a half wave rectifier we require only one diode, my dear. We require just one diode. How it operates, you already know this now, you already learned. I know that if you are a BTech student, you already know that. If you are a diploma student now, you have to learn from the basic, but for a BTech student we learn it from many situations where it crosses, right? This half wave rectifier, full wave rectifier and all we learn, but some important terms now that we really chances of error will be very high there. That only I am going to mention, especially the peak inverse voltage and all. Okay, that definitely you will make an error in the peak inverse voltage. I know, even myself itself I make some errors there. No, make confusion there. Peak inverse, or what is the value in that. And some important terms also we are going to discuss. Okay, we are taking the classes for entirely on the basis of the examination point of view, my dear, not for the university exam. Okay, remember that. So listen, so half wave rectifier is nothing but, my dear, we require only one diode. So let's see the working of this one. So for this AC input wave is nothing but, my dear, this is the nature, right? This is the nature. It have both positive as well as the negative half cycle. So for positive half cycle, this is nothing but it may be a step down transformer or step up transformer depending upon the application. Commonly it may be a step down transformer because this diode withstand that much voltage, right? Unless it's a power diode. Power diode can withstand any value, no problem. But if you're using a normal diode, its voltage level will be very limited. So normally we are using a step down transformer, that's all. So for positive half cycle, my dear, this term will be the winding, this side will be plus and this side will be minus. Okay. What is mean by plus and what is mean by minus means? Plus means current in one direction, minus means current in opposite direction. That is the meaning of plus and minus. Okay, don't worry. So what happened, my dear? Positive half cycle, this is the positive half cycle, or this is the symbol, I mean this is the polarity of the positive half cycle. This term will be plus and this term will be minus. Normally we are taking that convention. So what happened? The diode got forward bias, right? We know this. When positive is connected to P and negative connected to N, the diode got forward biased. So what happened? Only a very few resistance will be offered by the diode. That is called the forward resistance of the diode, which is represented by RF. We already know this RF. No? We already know that RF. But if you consider this an ideal diode, definitely there will not be any resistance, such resistance. Simply to act as a short circuit, it will conduct fully. So what is happening here? The half cycle will be available here. Half cycle means nothing but there will be a flow of current in the positive half cycle. So if you observe the waveform, my dears, so we will get a complete half cycle. That means what half cycle is here, exactly it produces here, that half cycle. So what happened in the negative half cycle? So negative half cycle, my dear, this term will be now minus and this side will be plus now. So what happened? Minus to P means it is reverse biased, we know that. Minus to P means it's reverse biased, and plus to N means also reverse biased. So what happened? The diode will be simply act as an open circuit. The diode will be simply act as an open circuit, means there will not be any current flow, which means there will not be any voltage across the load resistor RL. So what happened? For negative half cycle, my dears, for negative half cycle, there is nothing in the output voltage or output current, because the diode is not conducting here. The diode simply acts as an open circuit. So what happened? There will not be anything. There will not be anything, as well as for voltage, as well as for the current. There will not be anything. And what is the next half cycle again? This thing will be repeat again. For next positive half cycle, this term will come. So diode will be forward biased. The waveform will be obtained there. So what happened here? Listen. So we can say that, my dear, we can postulate, or we can summarize some important thing here from the half wave rectifier point of view. Of course, we know that the output is unidirectional. Am I right? The output is what, my dear? Unidirectional, because there is no negative sides. There is no negative waveforms. So you can say that the output is unidirectional. The output is not pure DC, but a pulsating DC, right? Am I right, my dear? The output is not a pure DC, because pure DC means it should be like this. That is the purest DC obtained from a battery. But this is not the pure DC now. This is containing a pulsation, right? It contains some AC component also, right? We will discuss that components and everything later. But just we noted that output not pure DC, but pulsating DC. Next one. The frequency of output voltage or current same as input. That means F0 will be equal to F input. F0 will be equal to F input. Okay? Did you know this? Did you note this? Can I erase this, my dears? Okay. And what is the next point, my dear? What is the next point? What is the next point? What is the next point? There is another important term you have to note always, my dear. Peak inverse voltage. So what do you mean by peak inverse voltage? What do you mean by peak inverse voltage? It is actually reverse. I will try to write the definition first. It is the maximum reverse voltage or maximum voltage available across the diode when it is reverse biased. Okay, that means nothing but, my dear, it is the maximum voltage available across the diode when it is in reverse biased condition. This term is very, very important, my dear. Okay, what is mean by peak inverse voltage means, when forward biased, we know that the diode is simply conducting, there will not be any drop, there will not be any problem. Okay, but reverse, when the polarity changes, what means the conductor become, the diode become reverse biased. So it simply act as an open circuit terminal. That means the diode itself will block the negative half cycle. That is the meaning now. So what happened, my dear, when it block the input current or input voltage, what will be the voltage or current available at its terminals? That is called the peak inverse voltage. So we know that under reverse biased condition, my dear, it simply act as an open circuit. I already discussed that. So what is the voltage available here? What is the voltage available here is called the V peak inverse or VPIV or VPAV. So this is the voltage available here as the peak inverse voltage. So what is the voltage available here, my dear? Simply the terminal voltage now. What is the voltage available? If you took a voltmeter and you put two terminals here, what voltage you will measure? You will measure exactly the same voltage now, right? If it is an open circuit, you will definitely measure the two terminal voltage itself. Suppose this is the input voltage that we are applied. Okay, it having some value and the output voltage having a maximum value of Vm. Okay, imagine the maximum value of Vm. Imagine the maximum value as same as Vm. Suppose the transformation is simply the same voltage it produces in secondary also. Imagine, suppose the voltage across this secondary terminal, maximum voltage across the secondary terminal will be Vm. Okay, imagine, then the peak inverse voltage is nothing but the same Vm will be available. Same Vm will be available. So I can write like peak inverse voltage will be equal to Vm, where Vm is nothing but, my dear, maximum value of voltage available at the secondary of transformer. Secondary of transformer. That is the concept of what, my dear? Peak inverse voltage. Okay, so that are the important points you have to note from the point of view of half wave rectifier. Okay, let's now move on to the efficiency of a half wave rectifier. This is also very, very important, my dear. This is also very, very important. Efficiency of half wave rectifier. Next, you have to say the efficiency. Efficiency. Let me check the time. Okay. So what is mean by efficiency, my dear? Efficiency is nothing but output by input. Here the output is nothing but, my dear, the DC, right? The DC power is the output power. in a consider this as a rectifier. Okay, hold the system a rectifier system. Efficiency in the sense rectification efficiency. Okay, other efficiencies also there, we will discuss later. I mean, the next question itself we will give you the answer of other type of efficiency, but now it is the efficiency means simply the rectification efficiency. Okay, I will write that directly, my dear, otherwise it will make confusion with respect to other other efficiency. So rectification efficiency, which is nothing but, my dears, PDC divided by PAC, because DC is nothing but direct current, that is the output is nothing but the direct current, right? So the output direct current power divided by what we are applying, input current, right? So input, it is nothing but the AC. So the output produced is nothing but the DC, but the input that we are given is nothing but the AC. So the output power by input power gives the value of efficiency. So what is PDC, my dear? PDC, which is nothing but, my dear, IDC the whole square into RL. Am I right? Because across the load we are taking the current or voltage, right? So it is nothing but IDC the whole square into RL. IDC the whole square into RL. For half wave rectification or for half wave rectifier, we already know what is IDC now. IDC is what, my dear? For a half wave rectifier, IDC is what? What is the equation for the DC value or the average value? Is nothing but, my dear, 1 by 2 pi into integral 0 to pi into IDC, na? So it will be, I will write like Vm divided by Rf plus RL, right? This is I square. So RMS value, na? Simply I into sin theta d theta. Am I right? It is actually this Vm sin theta is come here. Vm sin theta. Okay, correct, na? Vm sin theta d theta. Okay, how it obtained, I will explain. See, IDC, general equation for finding the average value or DC value is nothing but, my dear, 1 by 2 pi integral 0 to t. 0 to time period here, na? Here the rectifier output you observed, na? So what is the rectifier output? So this is the pi and this is 2 pi, but the rectifier output is only for pi. This will repeat after only 2 pi. 2 pi. So pi. Okay, so considering the whole time period is nothing but, my dear, whole t. In the output, only not for whole t the output is obtained, only for this time only the output is obtained, right? For not whole t the output is obtained in the half wave rectification, but only for 0 to pi the output is obtained. That is why in the equation of average value, 1 by t, 1 by time period, there is no change, my dear, it is 1 by 2 pi, but because the time period is nothing but 2 pi, there is no change. But from what to what the output is there, that is called this limit. So 0 to pi only the output is there, that output is nothing but, my dear, Im sin theta, simply. This value is nothing but, my dear, Im sin theta. But what is Im now? Im is nothing but, my dear, Vm divided by Rf plus RL. Im is nothing but Vm divided by Rf plus RL, where Rf is the forward resistance of the diode, RL is the load resistance of the diode, load resistance of the rectifier, that's all. Is it clear? There is no confusion at all, right? So this will be the equation Vm sin theta divided by Rf plus RL, that is the IDC. Okay, well, how it obtained, we will solve it. So Vm divided by Rf plus RL, simply I will take like Im. So Im by 2 pi, there will not be any change. Sin theta is nothing but minus cos theta. I am taking it minus outside and 0 to pi. So which is nothing but, my dear, minus Im by 2 pi. Okay, minus 1 minus 1. So minus and minus get cancelled, simply Im by pi. So that is nothing but the IDC. That is nothing but the IDC. So what will be PDC now? IDC square, right? IDC square into RL. So which is nothing but, my dear, Im by pi the whole square into RL. Okay, Im by pi the whole square into RL. Is it clear, my dears? Is it clear? Okay, So what we will obtain now? We got PDC, right? Then PAC. What is that PAC now? PAC is nothing but, my dear, IRMS square into RF plus RL. Am I right? Because we are giving the input power, right? Input power is nothing but input voltage into input current. The input current feels a resistance of this much, right? PAC is nothing, power is nothing but, my dear, I square into R. We are given the input power. So input current into input resistance. What are the input resistances now? RF and RL. Is it clear? RF and RL will be the input resistance. So it will be like PAC is equal to IRMS square into RF plus RL. Then what is the IRMS value? What is the RMS value? You already know. Definition of 1 by root of this thing. I will explain that also. 1 by 2 pi integral 0 to pi into Im sin theta the whole square d theta. If you solve this, you will definitely get, it is nothing but minus Im by 2. That is nothing but IR. So you solve, you can be able to get. So the efficiency is nothing but, my dear, PDC by PAC, which is nothing but, what is the PDC? What is PDC? This term will be there, RF plus RL. This also there. Okay, this also there. So what do you get now? Yeah. What do you get now? PDC. PDC is nothing but, my dear, Im divided by pi the whole square into RL whole divided by Im divided by 2 the whole square into RF plus RL. Am I right? IMR square into RF plus RL. Okay, this will not be there. This will not be there. IRMS square into RF plus RL. Na? IRMS is nothing but 1 by 2 into Im sin theta d theta. Simply it will get I by 2. So efficiency is nothing but Im by pi the whole square into RL divided by IRMS square. That is Im by 2 the whole square into this term RF plus RL. Okay. So if you took the RL outside in the denominator, what I get, my dear? Im by pi the whole square into RL whole divided by RL into Im by 2 the whole square into, what is that? RF by RL plus 1. RF by RL plus 1. So this RL and this RL get cancelled. Okay. I will derive here. Okay. I will derive here. The remaining will be here. So what I get? This Im square and Im square got cancel. 4 by pi. Am I right, my dear? 4 by pi. Because 4 by pi square, right? This 2 square goes out open. So it will be 4 divided by pi square. And denominator is nothing but, my dear, RF by RL plus 1. The value of RF is very, very less. But RF very, very less than RL. So this RF by RL will be very less compared to 1. So this term can be avoided. This term can be what, my dear? Avoided. So percentage efficiency is nothing but, my dear, approximately 4 by pi square into 100. If you solve this, you will get 40.6%. Solve, you will get 40.6%. That's all. Yeah. You will get 40.6%. Is there any doubt? Is there any doubt, my dear? This value is very, very important. This value is very, very important. Okay, note it down. You need not to remember all this derivation and all. It's for your understanding, my dear. But this value is for half wave rectifier, the rectification efficiency is nothing but 40.6%. Is it clear? Is it clear, my dears? Is there any doubt? You can comment. Okay, you can comment. And let's do a beautiful problem so that we will learn very, very important term regarding the diode rectifier that you already didn't learn. Okay, you already didn't learn. Okay. write a question, my dear. We will. The applied input AC power to a half wave rectifier is watt. The DC power obtained is 40 watt. A. What is the rectification efficiency? What is the rectification efficiency? What is the power efficiency? Very important concept you are going to learn, my dear. Very important concept. See, the applied input AC power to a half wave rectifier is 100 volt. 100 volt. That means the applied AC input is nothing but, my dear, PAC. So PAC is nothing but, my dear, 100 volt. PAC is nothing but IRMS curve into RF plus RL. Am I right? That is nothing but, my dear, 100 watt. The DC power obtained is 40 watt. That is nothing but PDC is equal to what, my dear? 40 watt. So what is the rectification efficiency? Simple. What is the rectification efficiency? Rectification efficiency is equal to what, my dear? 40 divided by 100 into 100. Am I right? Output is nothing but 40, input is nothing but 100. So 40 by 100 into 100 will cancel 40% efficiency. We know that maximum efficiency will be 40.6. It's less than 40.6. So okay, 40% efficiency. Next efficiency is very important, which is nothing but, my dear, power efficiency. Power efficiency. Okay, let it be eta dash. So the power efficiency, the term power efficiency is nothing but, my dear, again the output power to the input power, to the input power. Okay, but the powers are slightly different. I will tell that. See, my dear, the applied input AC power to a half wave rectifier is 100 watt. That means we are applying this much power, my dear. Okay, this is the full wave rectifier input. This is the input now. This is V input. Okay, this is the input. So the power we are applying here is nothing but the full wave power. Suppose this is the power waveform, P, input power waveform. Okay, so we are applying the full wave power. 100 watt means nothing but, my dear, for positive half cycle it's 50 watt, for negative half cycle it's 50 watt. This is you are learning. I think it's new to you. So total power is, total input power, the applied input AC power to a half wave is 100 watt. Input is nothing but the pure AC sine wave. Pure AC sine wave. So from these, 50 watt is for what, my dear? 50 watt is for the positive half cycle and another 50 watt for the negative half cycle. Am I right? So from this 50 and 50 configuration, what is the value of power only available to the rectification? For rectification purpose, what power is only available? What power is only available? The only power is nothing but the power of positive half cycle is only available for the process of rectification, right? The diode, in the diode. The diode utilize only the power of this 50 watt. You might have think that, sir, we are giving 100 watt, okay, and the output is only 40 watt. Rest of 60 watt is where? That answer is here. That answer is here. So the input power is nothing but 50 watt and 50 watt configuration. So only this 50 watt is available to the diode for conversion. So clear? Only that 50 watt is available to the diode for conversion purpose. So what my diode is doing? It converts simply the 50 watt. It converts simply the 50 watt and produce the 40 watt output. And the remaining 50 watt is not at all available to the diode. Not at all available because it block that 50 watt. It is not available. Array, I don't need that 50 watt. I need only positive half cycle. The diode will reply. So the diode will simply look at that negative 50 watt and simply reject it. Simply reject. So the term power efficiency is nothing but, my dear, the power available, the power output from the diode to the power input to the diode. That is called the power efficiency. So the power output to the diode is nothing but, my dear, 40 watt. Power input to the diode is nothing but, my dear, 50 into 100. So it is nothing but, my dear, 2. So 80%. So that is the rectification efficiency and power efficiency difference. So rectification efficiency means consider it's the whole rectifier system. Power efficiency means consider only upon the diode. So what is the power? I mean diode's power efficiency. That is the term means you have to focus on the diode only. What is the power available to the diode? Not from the input side. I don't want to know what is happening in the input. I just want to know what is the diode input, what is the diode output power. That's all. So the diode only receives 50 watt and it produces 40 watt from that 50 watt supply. Only 10 watt is loss. Okay, that's fine, no problem. So this is a very, very interesting concept, my dear. Okay, so for that only I did this problem. So that's all about the half wave rectifier.